Hey guys, we're going to look at quadratic function graphs today for our distance learning day because this is something I think that you'll be able to catch on to pretty easily at home. We've done quite a bit of this already, so most of this will be review. There will be a small portion of it that is new. So by the end of this, you'll be reminded of how to identify the characteristics of quadratic function graphs and describe transformations of them. So you know a lot about these characteristics already. You learned a lot about transformations last year as 8th graders, so some of this will be new for these function graphs, but it'll be the same concepts as what you learned last year in 8th grade about transformations. So hopefully most of this will catch on pretty easily for you. All right, so here are the characteristics of quadratic function graphs that you need to be able to recognize. The first one is the vertex, and that is either the lowest or the highest sometimes, but it's the turning point of the U or the V where the graph changes direction. So it's expressed as an ordered pair. They call it H comma K, but it's an ordered pair that is that point. So if you've got a U-shaped graph, the vertex is the very bottom of that U. Or if you have a V-shaped graph, same thing. Or if it's upside down, same situation. It's the bottom, the very bottom point, or the very top point where that U or that V changes direction. Now, we've done maximum and minimums before. For these quadratic functions, there's always going to be a maximum or a minimum. That's either your highest or your lowest point. They'll always tell the Y value from that point. So if they ask you what the maximum is, it's whatever the maximum is in the Y position, or the minimum in the Y position. Now, we talked about symmetry before and whether functions were even, odd, or neither. But we never talked about the actual axis of symmetry for a quadratic function because I figured we would wait and save that for this particular lesson here. But the axis of symmetry is an imaginary line oh, sorry. I'm like, why does it say line? Just kidding. An imaginary vertical line. Now remember, vertical means up and down. Through the vertex that evenly splits the graph into two equal sides. That splits the graph into two equal sides. It is always written as x equals h. So if in your vertex it's written as h comma k, the x value from your vertex is the value that is in your axis of symmetry. It's always x equals, and that number that's going to go there is going to be the x value of your vertex. All right. Then zeros, and we've talked about zeros before. Remember, those are your x-intercepts. Or the places where the graph crosses the x-axis. And then, of course, a y-intercept is the point where the graph touches the y-axis. So the only thing from any of this that is new for you is a vertex and the idea of this axis of symmetry. The other things are things we've already done before. Hopefully some of that is familiar to you. So when you're describing these characteristics, you've got to be able to look at the graph of the function. So you're either going to graph an equation that's given to you, or if they give you a graph already, you can just look at it and identify that information from it. But if they don't, they just give you like the function equation, put it in Desmos, and then look for these things. As long as you know what you're looking for, you don't have to do the graphing and stuff by hand, which is great. So let's look at an example of this. And they've given us a graph here. They've given us 2 points on the graph. Which may or may not matter to us, but we're looking to describe the vertex of this graph, the maximum or minimum, the axis of symmetry, the zeros, and the y-intercept. So looking at this graph, remember, a vertex is the point at the turning point of the U or the V. So if I'm looking at this, the vertex is going to be located right here in that bottom position of that parabola. So that bottommost point is my vertex. The coordinates of that point are 1, -1. So my vertex is located at 1, -1. Now, because it's a quadratic function, it's going to have a maximum or minimum. This one in particular has a minimum. And I know it has a minimum because it has a lowest point. It does not have a highest point because it keeps going up forever. But it does have a lowest point. So we have a minimum. That minimum is located at the vertex. So the vertex is going to be the maximum or minimum. You have to decide which it is. And then the value you get from it is just the y value. So we have a minimum of -1 in this function, because that is the y value from my vertex. Now, the axis of symmetry also involves the vertex. It is an imaginary line that goes through the vertex vertically. So it's the line that would go here and split this in two. That's always written as x equals. And it is always written as x equals whatever the x value is from your vertex, or the h value in that hk vertex. So for this one, x equals 1. If you're not sure if it's supposed to be x or y equals, you can always graph that in Desmos too and make sure it goes in the right spot if you need to. Now, zeros are the points where it touches the x-axis. So zeros and x-intercepts are the same thing. So for this, we touch the x-axis right here, and then again right here. So there are two zeros. Those zeros are located at 0 and at 2. Sometimes you'll see that given as just the number. Sometimes you'll see that given as an actual ordered pair, like 0, 0 and 2, 0. It kind of depends on how the question asks for it. And then our y-intercept is the point where it touches the y-axis. So my y-axis, remember, is the vertical one. It touches the y-axis right here at 0, 0. So we're just identifying those characteristics. All right, let's look at another one. Same deal, we're looking for all those same things. So I'm going to identify my vertex, which is my point right here where it changes direction. That's located at -1, 2. So this particular function has a maximum, and I know it's a maximum because it's a highest point, and that's located at 2, because that's the y value for this point. And then we've got an axis of symmetry that'll go vertically right through here. So that axis of symmetry is going to be x equals -1. So notice that your maximum or minimum comes from the y value of your vertex, and your axis of symmetry comes from the x value of your vertex. That's going to happen every time. For us to identify the zeros of this, I've got to look at my x-axis. It touches right here and right here. Now, I can't tell exactly perfectly for sure on this what those numbers are. I'm going to estimate about -2.5, because to me this point right here looks to be between -2 and -3, about halfway. It might be a hair less than halfway, but it's pretty close. And then this one over here is a little less, I think, than 0.5, maybe 0.4, 0.3, something like that. So 0.4 will be the other one. So again, you might see that as points, -2.5, 0, and 0.4, 0, or you could see it as just the numbers. And then this crosses the y-axis vertically right here at +1, so 0, 1. Alright. Take a minute and try this one, and then unpause the video, or pause the video, try this one, and then come back and see if you were correct. Okay, take a look at that and see if you got the same things that I got for your answers there. Just be reminded that when you're coming up with your maximum or minimum, and I forgot to highlight this should have been a maximum at 3, because that's our highest value for that vertex. Your axis of symmetry was the line that would exist at x equals 4. And then these were zeros. I kind of estimated those, but I think that's about right. And then our y-intercept, of course, was this point down here. All right. So now we've got some that we don't have a graph for. So we're going to have to put these in Desmos to be able to see what the graph looks like and still identify this information from it. So I'm going to grab Desmos real quick. Oops. And I'm going to put this first one in, 2x squared plus 4x. And look, if you're just graphing the parabola and not having to compare it with anything, you don't have to put the y equals. It'll graph it without that part. So here I'm looking at my parabola. Now, the good thing about Desmos is you can tap the vertex, and it's going to tell you exactly what it is. So -1, -2. So if I know my vertex, I can look at the shape of that and recognize that that is a minimum. It's a low point. Maximum would be for the upside down ones, but this one has a smiley face, so it has a minimum. And that minimum is located at -2. It's the y value for that. The axis of symmetry there is going to be that imaginary line that I could draw through the vertex, located at x equals -1. Again, those come straight from the vertex, those numbers do. This has 2 zeros. Another good thing about Desmos is you can tap the zeros, and it's going to tell you exactly what they are. Maybe. I can't do it in this moment because... Anyway, if you could do it, which you could if you were looking at it on your pad, it would tell you exactly those points. So I see that I've got a point at -2, 0. And I have another point at 0, 0. Those are my 2 zeros. And then the y-intercept here is also located at 0, 0. So this is pretty simple, identifying those things. If you don't have a graph of it, then you're going to create the graph in Desmos and then look at it from there. All right, let's do this next one. -x squared plus 4x minus 5. -x squared plus 4x minus 5. All right, there's my parabola. It's a sad face parabola this time, upside down. So my vertex is still that changing point, that point where it turns. So for this one, it's 2, -1, which is a maximum for this one because it's an upside down parabola. It has a high point, not a low point. So my maximum is going to exist at -1. My axis of symmetry is going to be x equals 2. It has no zeros. Notice that it never touches the x-axis, so there are none. And it has a y-intercept at 0, -5, because I see where it's touching my y-axis at -5. So take just a minute, pause the video, and go graph these in Desmos and see if you can identify this information for that. And then unpause the video and come back and see if you were correct. All right, take a look at those and see if you got correct answers for each one. If you missed something, maybe pull back up the graph and look at it and see if you can see where I got my answers compared with what you chose, so that you can see maybe what you did wrong there. Anyway, hopefully that's pretty clear for you and pretty easy for the most part. So now let's look at how this applies in a word problem situation, which again is not terribly difficult, but we need to kind of understand some basic ideas of what they're actually asking for in those. So if you're looking at a word problem and it's involving a quadratic equation, it usually has a whole bunch of words, and then it usually will give you a graph. Or it has a whole bunch of words and it'll give you a function to represent it. So here's what you want to know. If they ask you for the highest point, they're asking you for the maximum y value. If they ask you for the initial value or the starting value, they're asking you for a y-intercept. If they ask you when it will hit the ground, they're asking you for the second 0. If they ask when will it reach the maximum or when will it change directions, they're asking you for the vertex. All right, let's look at how this works in an actual problem. So this says, suppose a particular star is projected from a firework at a starting height of 520 feet with an initial upward velocity of 72 feet per second. The equation h equals 16t squared plus 72t plus 520 gives the star's height in feet at time t seconds. So we've got to graph this to be able to figure out the answers to these questions. How long will it take the star to reach its maximum height? What is the star's maximum height? So we're looking for how long it takes to reach the maximum and what the maximum actually is. So basically, we need a maximum for this. Now, I made a mistake in creating this. This should have been a negative 16t squared. That's my fault. So I just have a little negative in there, and then we're going to pull this up on our Desmos graphing calculator so we can look at it. So I'm going to put that equation in, negative 16. Now, it says t. You can put x in there. Negative 16x squared plus 72x plus 520. Okay, so I've got this big old giant parabola. And I can't see the whole thing, so I'm going to have to zoom out a lot. I'm only going to pinch down to zoom so I can get higher, but not as wide if I can help it. Although that's not working, is it? Anyway, here it is, sort of. All right. So I'm looking for the maximum. So I know the maximum is represented by that vertex right there. My maximum is at 601 feet, right? Because that's what my vertical is representing here. They want to know how long it will take to reach that maximum. The x value represents time because it says feet per second. So feet is y, seconds are x. So that 2.25 is going to be my time. 2.25 seconds to reach a maximum height of 601 feet. That's what that vertex tells me. All right. This one says the total profit made by an engineering firm is given by the equation P equals negative x squared plus 24x plus 5,000. If x is the number of clients the firm has and P is the profit, find the maximum profit made by the company. So again, if I want to see that maximum, I'm going to graph it and find the highest point. So negative x squared plus 24x plus 5,000. Negative x squared plus 24x plus 5 grand. All right. And so somewhere in here, far, far away. And look, sometimes with these word problems, you're going to get these really large parabolas. But if you can just zoom until you get where you need to get with it. My maximum value is located at this point, 12, 5,144. They're just asking about the profit. So what this is telling me is that with 12 clients, they reach a profit of, I don't know what I touched there, but anyway, it wasn't intentional. $5,144. So the maximum profit is $5,144. All right, another one. You and a friend are hiking in the mountains. You want to climb a ledge that is 20 feet high. The height of the grappling hook you throw is given by the function h equals 16t squared plus 32t plus 5. What is the maximum height of the grappling hook? Can you throw it high enough to reach the ledge? So we got to answer really two questions here. Again, about a maximum. So I need to be able to see the graph of it to be able to tell what the maximum would be. So negative 16x squared plus 32x plus 5. All right, so to find my maximum, I'm going to zoom out. Look for that point at 121. Sorry, y'all, distraction. So my maximum is located at 121. So the maximum height of the hook is 21 feet. The question is, could we throw it high enough to reach the ledge? So if the ledge, and it tells me right here that the ledge is 20 feet high, If our maximum height is 21, then apparently we can, because we threw it 21 feet here. So, to answer a question of can we? Yes, we can. All right, take a minute. See if you can figure out an answer to this one. If you've not paused this video, pause the video, work the question, then come back. All right, so with this one, when you worked it out, you should have gotten this point as your vertex, which means the maximum height from that is 2.25 feet. The Y value is your maximum. So the question was, will you be able to dunk the basketball? If you have to be able to jump 2.5 feet to be able to dunk it, and you can only go 2.25, no, you could not dunk it. All right. Hopefully you got that correct. If you didn't get that as your maximum, maybe go back and check what you graphed. You could have made a mistake in what you typed in. All right, and then the last thing we need to look at, and this looks complicated, but it really is not, is how to transform quadratic functions. So a lot of quadratic functions are written in that x squared plus bx plus c format, which is considered standard form. You can also write them in vertex form, which looks like this. Y equals x minus h squared plus k. If you have one written in vertex form, you can see from that what or actually there should be an a right here too. A, x minus h squared plus k. And the h and the k right there represent your vertex. Remember, a vertex is h comma k. So notice the h got a minus in front of it, so it's really like the opposite of h and k. But you can see the vertex there. You also could see a number out front sometimes that represents either changing it by multiplying it by a certain value. And that's going to kind of change the size of it. So it's possible to transform a function by changing the a, the h, or the k. So in 8th grade, you learned about different types of transformations. You learned about translations, which hopefully you remember to be slides. So translation is a slide. That means you just slide left or right, you slide up or down. So if you're going to translate something horizontally, that means you're changing the x values on it. Right? So moving left or right changes the x. So in this function, the letter that represents the x value of your point is the h. So you can change the h, and that's going to cause that to shift left or right. If you want it to shift to the left, you're going to add to move to the left. Oops. If you want it to shift to the right, you're going to subtract to move it to the right, which seems opposite of what it should be, but because that number represents the opposite of h, adding and subtracting opposite works like that. Now, if you're going to change it vertically, slide it vertically, that would be sliding up or down. You're going to change the k. Add to move up, subtract to move down. Then you got to also be able to reflect. Now, hopefully you remember reflections or flips. You're only going to reflect vertically. All you have to do is change the sign of A. So if A is positive, you're going to have a parabola that opens up. If you have a negative A, you're going to have a parabola that opens down. Sad face when it's negative, happy face when it's positive. And then you have a stretch or a compression. This is like a dilation, where you're changing the size. And you do that by changing the A. If you want your graph to get wider, so if it's like this and you want it to be wider, then you're going to change your A to be less than, really between 0 and 1, not less than 1. So it's got to be a fraction, basically. So A is going to be between 0 and 1. To make it steeper, so if you're here and you want it to get more like this, slenderer but steeper, then you're going to have an A that's greater than 1, because that's going to allow your numbers to rise faster, causing your graph to become steeper. So it's called a compression when it gets wider. It's called a stretch when it gets steeper. I should have made a line for that, and I didn't. That's my fault. So when you see it get wider, that's a compression. Kind of like if you stepped on a can, it would flatten out, but it would get wider than it was when it started. Or if you stepped on like a wad of Play-Doh, it would flatten out but go wider. And then a stretch is when it gets longer but skinnier. All right, let's look at this then. And I know I might be going fast. You can always pause the video if you need to. So if we're going to look at this, they're usually going to give you a parent function, which is the one you're comparing everything to. And then they're going to ask you to describe how something was transformed. So the parent function, and this applies to things other than quadratics. It could be anything. But the parent function here is going to be x squared, and we're going to look at how each of these changes from x squared. So you're going to want Desmos. And we're going to graph x squared first. And then I'm going to graph each function that I'm looking at. So x minus 2 squared is the first one. So when I look at that, now remember the red one is my parent function. So I want to look at how the blue for my graph changed from where it was on the red. And so I can see with this that my blue function shifted 2 units to the right. So the graph itself didn't change. The size of it is still the same. I don't mean to be zooming like that. I'm trying to zoom Desmos and I'm failing epically. In ways you can kind of see that. I'm still not doing what I'm trying to do here, y'all. Okay, there we go. The way you can see that the size of the graph itself didn't change would be by looking at some specific points. Like notice across the bottom here that I'm 2 units wide on the red one. I'm still 2 units wide on the blue. So I didn't get any wider or steeper or anything like that. But what I did do is see this thing shift over from 0 to be now located at 2. So when I'm describing that transformation, that's a translation 2 units to the right. All right, so I'm done looking at that one. Now let's look at the next one. So I'm still keeping x squared as my parent function, and now I'm comparing 2x squared to that. Now notice the red one and the blue one now. So remember, we're looking at how did the blue change from the red. Now the vertex is still located in the same place, so it didn't slide left, right, up, and down. It didn't flip over, so no, there's not a reflection, but it changed size, so that's a dilation or a stretch or a compression. We've got to decide which it is. So remember, it's a stretch if the new one gets slimmer, goes up faster than the old one. It's a compression if the new one is wider than the old one. So if the blue one is my new one, it is not as wide as the red one was, which means this thing has been stretched vertically. So it's a vertical stretch. And it's by a factor of 2 if they ask you that. That 2 gives you how much it's stretched by, the factor of 2. All right, let's look at one more of these together. Maybe. Fighting with Desmos here, y'all. All right, x plus 3 squared minus 4. There's my original is the red still. My new one is now green. So I want to see how did my red become my green. So I've got to ask myself, first of all, I see that the vertex has moved. So I see that I went from here to here. So definitely had a slide of some sort. And I see that I translated left and down. Let's see if the sizing of this thing changed. So we can tell that by looking again at the width of it. So the red one is still 2 units wide. If I go to that same spot on the green one, 1 unit up from the vertex, still 2 units wide. So there was not any kind of compression or stretch here. So just a slide, it didn't flip over. So when I describe this, I'm going to describe it as a translation. And it looks to me like it went 1, 2, 3 units to the left and 1, 2, 3, 4 units down. We'll do a couple more of these. Now looking at this one, some of these you can even tell, if you don't want to have to graph the parent function in the new one, you could even maybe just look at this and see what has happened to it. We see that if we're thinking about this vertex form, remember, changing this number causes it to move left or right. Changing the K causes it to move up or down. Changing the A causes a stretch or a compression. So looking at this, if I put a 3 in place of A, I know that there's going to be a stretch by a factor of 3. If I add 1 to this, I know that's going to cause me to move left, a translation, left 1 unit. Now you can graph that in Desmos and see that, but you might also be able to get yourself in the habit of just looking at the function that you're given compared with, especially if it's in vertex form, to be able to see what has happened to it. So like this one, for example, I see that my x squared has been made negative, which means it's had a reflection. I also see that 3 has been subtracted from the end, which means we've changed vertically. So a translation down 3 units. Again, you could graph that in Desmos to see that. I'm not telling you not to do that, but I am saying that you might save yourself some time if you can kind of learn how to read through these. So for this one, I've got a change in A, I've got a change in my H, and a change in my K. So a lot of things are happening here. So I've got a reflection because my A is negative. I have a vertical stretch. By a factor of 2 because my A is a 2 instead of not being there at all. I've got a horizontal translation. Remember, when we're adding 2, we're actually moving left. And 4, because I have a 4 there at the end. And again, you could see all of that by putting that in Desmos if you wanted to. But that's another option for you there. All right. Take a minute, and however you need to do it, go through and figure out the transformations from the original x squared into these new forms. And then come back and see if you were right. Make sure you pause the video to try those out. All right, take a look at that and see if what you got matches what I got. So the first one's just a simple translation. The only thing that changed from original form. Should have wrote this down before we started. Ax minus h squared plus k. The only thing that changed was the h, and so the h causes you to move left or right. That would be right to 8. This one had a reflection of, because it has a negative here, a stretch by 3. A slide to the left, 4. This one had a stretch of 2, a slide right 1, translation right 1, and a slide up 6. So you need to be able to look at that either from the equation itself or by graphing it in Desmos and looking at it to get those changes that occur from that. All right, that is the end of our little lesson. Y'all have a great day.